Okay, so last class we started doing a little bit of a review on our thermodynamics, and we said that, well, we haven't used the word thermodynamics a lot, but thermodynamics is the study of delta H. So we reviewed how we would answer this question, right? These questions, we would take products, the delta H formation of the products minus the delta H of formation of the reactants, and that would result in the delta H for this reaction, right? Same thing for any of these reactions. And we did some practice problems. Also, we talked about how the total energy, delta H, is just the heat energy, but there's two ways of releasing energy. One is the heat, and the other is the work. And usually that's identifiable by the expansion or the contraction if work is being done by the surroundings on the system. Okay, so work is defined by this little tidbit of information, looking at the change in the moles of gas in a chemical reaction. So moles of gas in the product side minus moles of gas in the reactant side, and you only choose the gas components, right? Change in moles times R, which is this 8.314 joules per mole, Kelvin, divided by, times the temperature in Kelvin. And then we throw in a negative sign. That way, if it's negative, it means the reaction is releasing energy, right? Releasing that work energy. Okay, and we said that the combination of the heat and the work, delta H, and the work energy is the total energy, or delta E. And so we have the ability to answer delta H for a chemical reaction. We have the ability to answer the change in work energy, right? And then the combination of those is the total change in energy. Okay? Now, this is new stuff. Delta H and delta G, or delta H and delta E energies, that the two thermodynamic parameters that we've kind of been talking about thus far, they are temperature dependent. So at different temperatures, you'll get different delta H's and delta G's for a given chemical reaction. All right? So we have to kind of get information about the temperature and the conditions as well, because pressures also can alter chemical reactions based on if the products are more gaseous or less gaseous than the reactants, right? If you're at a higher pressure, then it's going to have a different kind of influence than if you're at a low pressure. So we have a little knot, we call it, little zero, it looks like. It's just a little knot that we put after our parameter, whether it's delta H, delta S, or delta G, E, right? Those are the two. Delta H and delta E are the two we've talked about. Well, we'll talk about delta S and delta G as well. But the knot there says we're at standard conditions, standard state, which is 1 atmosphere of pressure. Criminy, sorry about that. Here we go. So the delta H knot is the knot there is an indication that we're at standard conditions, standard temperature, standard pressure of 1 atmosphere. All right, standard temperature means room temperature, 25 degrees, 298 Kelvin. And solutions, if there's anything that's aqueous, is at 1 molar concentrations. All right, so that's what that little knot means there. And we kind of throw that in there because we're going to learn, if we have time. If we run out of time, we won't be able to, but we'll try to get into the influence of different temperatures on delta G's, delta H's, and delta E's, and other thermodynamic parameters that we'll introduce. Okay. A spontaneous reaction. Now, this is more of a definition that we're introducing, but basically what a spontaneous reaction is a reaction that will proceed from reactants to products simply by combining them together. You put them together and the reaction will proceed to products. And the two parameters that kind of determine whether that will happen is whether it releases energy in the form of heat or whether it releases energy in the form of work. Okay, so those two parameters will kind of come into play. But we call a reaction spontaneous if, when you mix it together, it releases a lot of energy, either in the form of work or in the form of, in the form of heat or in the form of work. Okay? Not always exothermic, but in general, overall, it has to release some energy some way to be considered spontaneous. Now, another parameter, another thermodynamic parameter that we want to introduce is called entropy. Entropy. Now, delta H, which we've talked a lot about in the past, right? Delta H is let me get a different pen. Oh, here we go. Maybe this will be a good one for today. Delta H is also known as enthalpy. Whoops. Enthalpy. Enthalpy. Now, this is not enthalpy here. This is entropy. Entropy. And usually at this point in your scientific career, you've heard or been introduced to entropy once or twice. And generally, we just kind of talk about entropy and say it's the measurement of randomness, the measurement of how random a situation or disordered situation is. So here's a little figure here to help us kind of think about that. Here we have low entropy. Low entropy. It's not random. All of the particles, members of the group, whatever they are, because this could be atoms of things, this could be molecules of gas or molecules of solution or whatever, but it could also be just, bowling balls or whatever, right? In terms of entropy, low entropy means there's lots of order, right? When we move over here, lots of randomness, lots of disorder, lots of ways that you can make these things kind of move around. Here, if this thing just moves up, right, left, down, you've got a variety of ways that this can move. But here, every one of these has the option of going right, left, up, or down, right? So you have a lot of different ways, a lot of different degrees in which energy can be released or motion can occur. All right, so entropy is kind of like Kelvin in terms of its measurement. We measure it from 0 up to, a very high number, as high as you want to go. Okay, Kelvin, again, 0 means no motion, and 0 entropy means no motion, perfect order. Okay, so these are all kind of relative to each other, these measurements of entropy. But as you get more entropically random or disordered, you have a higher entropy value, higher S value. Okay, so things that can affect entropy, right? Mixing, the volume change of a gas, right? Temperature is not a significant change if the state is the same, all right? So if we increase the temperature, but we don't actually go from solid to liquid or liquid to gas, then that temperature change doesn't really make a huge change. In the gaseous phase, it's less so. It can change things more so in the gas phase. The state, the number of particles, number of bonds, right? And like we said, the entropy of a pure crystalline solid at 0 Kelvin, we define as 0, okay? Not that we ever have this sort of a state necessarily, but that is where we would call 0 on the entropy scale. So it's always going up or down. All right, so what do you think? We would like to predict the sign for the delta S in the following. Delta is always final minus initial. So if we think about the the order of these reactions, the disorder of these reactions. Dry ice, solid, going to carbon dioxide gas, is this, which side here is more entropically random? The dry ice side or the carbon dioxide side? Well, the carbon dioxide is a gas. Each molecule is separate from each other, moving around, right? Here the carbon dioxide is a solid, so it's more ordered. So we don't have to know the exact numbers to know that this side is going to be a higher value. So if we said this is 100 and this is 50, just, choosing some numbers, a higher one and a lower one, then 100 minus 50 would put a negative sign on this delta S. Okay, negative delta S there. Moisture condenses on a cool window. Here we're going from gas to liquid, and so the liquid would have a lower number than the gas. Lower number, let's see, did I do this right? 100 minus 50, yeah. So lower this moisture condensing on a cool window. The cool window, if we said the cool window was at 100, and it was before it wasn't a gas, so 200. So the S, delta S here is going to be 100 minus 200. So it's going to be a negative value. Delta S is going to be negative. Let's look at this dry ice one. Make sure I did that one right. Solid to a gas, liquid, gas to a liquid, solid to a gas. So products minus reactants. Gas here, let's say if this was 100, the dry ice is more ordered. So it's 50. There we go. So this one is actually a positive delta S. So this is less ordered, the gas. This is more ordered. So that's a positive. This is a negative delta S. All right, the third one, AB going to A plus B. All right, in the A plus B, we have a higher amount of disorder. So if I gave that number 100, the lower amount of disorder would be 10. So products minus reactants, we're going to get a positive delta S here. Let's see, the next one, a drop of food coloring added to a glass of water. Okay, so in that case, there's the water and the food coloring together, and they have ways to interact, but they can't interact with each other until we mix them. Now that we can interact with each other, we have multiple ways in which they can interact, multiple intermolecular forces and so forth. So we would say the product side is more than the reactant side. So again, a positive delta S there. And then the last one there, what do we got? We got aluminum and bromine. This is a solid. This is a liquid coming together to form just a solid. So on the right here, and we only have two things on the right, 2 moles of material. Here we have 2 and 3, right? So this side, I would say, gets our higher number, whereas the right gets a lower number, because again, this is solid. There's only one of it. This is solid and liquid. There's only one thing, 2 of them. Here there's 2 things, 3 of this and 2 of that. So 10 minus the 100, this is going to be a negative delta S. Okay, so when we get a negative delta S, things are getting more ordered. Positive delta S, things are getting more disordered, right? So again, the dry ice going to carbon dioxide. Carbon dioxide is more disordered. It gets the higher number over the dry ice. Positive delta S if things are getting more disordered. Okay? All right. So why don't you guys take a look at this one, and in a few moments we'll ask Sarah to try to answer it for us. Try to answer it in your own mind first. Which of the following has the most entropy in standard conditions? Has the most entropy, highest value? And again, it's all relative to each other, so I just throw numbers in there to kind of give us an idea, especially when we're looking for the delta S. But here we're just looking for absolute S value. Okay, what do you think, Sarah? Which one would you say would have the higher entropy?
I would think H2O. Just, I know it's not AlCl because it's solid, but
okay.
H2O.
So H2, yeah, it has. It's a liquid, right? So because it's a liquid, things are moving around more, right? I think that that's the reason why we would say it's more higher than AlCl3, which is a solid. Good. What about NaCl aqueous? What about that one?
Yeah, I'm not sure on that one.
Okay. Well, NaCl aqueous, it has what? It has water in that mixture, right? We also have sodium ions, whoops, and we have chloride ions. And all of these things are interacting with each other, have the possibility to interact some way. If we compare that to just water by itself, then this mixture here has the ability to do whatever the water is going to do, but it also has the sodium and the chlorine. Can you see that, Sarah?
Yeah.
So our answer here would be C or B, because we have not just the water, but the sodium and the chlorine as well. Chloride as well. Okay, very good. So the second law of thermodynamics, we're not going to go over all this derivation here, but the second law of thermodynamics is a law that allows us to take into account, ultimately, looking here at the bottom, delta H, which is something we're familiar with, the change in heat of a chemical reaction, and it combines it with the delta S of a system. Okay, the delta S of a system can tell us about whether the system is becoming more disordered. And as things become more disordered, then in general, that means the reaction has a reason to proceed, or as it proceeds, the disorder itself prevents the reaction from going backwards, because as things become more disordered, it becomes harder to push the reaction backwards, right? So this statement here, delta H minus T delta S, is always going to be less than 0 for spontaneous reactions. And when it's greater than 0, then that tells us that the reaction is not spontaneous. So this law becomes helpful to us, especially when, delta H, we've talked about before, and we can say, okay, this reaction is going to release a lot of heat energy, but we've never really included the other component, which is this entropy. Because if a chemical reaction releases just a tiny bit of energy, then the entropy could actually be the step that would either force the reaction to occur or prevent the reaction from occurring if the delta H was very small amount of energy released. Okay? So the way that we get this to be negative is we throw in a negative sign here for the delta S of a system. All right, we just saw that if a process is getting more disordered, so looking at the S for the reactants, for example, and comparing that to the S of the products, if the products are more disordered, let's give it some value, S would equal 100, let's say. The reactants more ordered, let's give it a value of 10. The delta S for this reaction would be products minus reactants. Okay, so here we'd have a 90, positive 90. But that positive value is an indication that this reaction is becoming more disordered, and it becomes, that disordering process becomes a driving force for this reaction. So the driving force of the entropy and also the driving force of the heat released in a process are the two factors that will help us determine whether or not a chemical reaction is spontaneous. Okay? And so the delta S for this is positive, but we throw a negative sign in there because before we've said that negative delta H is an indication that the process releases energy. So that's why a negative value or value less than 0 is indicative of a spontaneous reaction. All right. And we provide a new thermodynamic parameter for this to have it all into one statement, which we call Gibbs free energy, delta G. Delta G. Delta G is a combination of the energy released in the form of heat and the entropy change in a chemical reaction, which takes into account the work as well. Okay, which was shown in this derivation back here. Okay, so this equation becomes basically our second law of thermodynamics. Delta G, which is a thermodynamic parameter of spontaneity, is equal to delta H minus temperature in Kelvin T delta S, minus T delta S. Okay? Now, this is will most likely be provided for you, or you can always try to look it up to remember it. But the big thing we want to remember, delta H, I think you guys have had plenty of experience with. And now we're introducing this delta S and this delta G. But the big thing we want to remember is that delta G is less than 0 when the reaction is spontaneous. It's a negative value if the reaction is spontaneous. Greater than 0 means the reaction is non-spontaneous, doesn't head towards products. At 0, if delta G equals 0, then the process is at equilibrium. Okay. So, we can have scenarios where delta H is a larger negative contributor to the delta G, but we can also have scenarios where the delta S is a larger, ultimately negative contributor, because this is a negative sign in here, to the delta G. So we can have reactions that we say are enthalpy driven or entropy driven. Enthalpy, again, is our delta H, our heat. Entropy is our degree of randomness. Okay? This can change at different temperatures because we see that T is in this second law of thermodynamics. T is multiplied, temperature is multiplied by the entropy, the change in entropy. Okay? So, if, for example, the delta H is a positive value. Now, if delta H is positive, what does that mean in terms of that a given chemical reaction? So let's have a chemical reaction here. A going to B, delta H is a positive value. What does that mean, Taewon? What does that mean? Do you remember? What does it mean when delta H is a positive value? That's right. It gets energy. The process requires energy. A, heat energy. A plus heat, right? Heat then acts as a reactant. Heat plus A goes to B if delta H is positive. For a reaction where, let's say, B goes to A and the delta H for this reaction is a negative value, that means heat is like a product for that reaction. Okay, so if delta H is some positive value, but delta S is positive also, meaning that it's possible to have a negative contribution because there's a negative sign in here. Positive value means it's becoming more entropically random, right? So if the delta S is a positive value as well, then, because there's this negative sign, it's still possible to get a negative delta G as long as the temperature is high enough to overcome whatever positive value here associated with this delta H. Okay, so you get this relationship here. If delta H is negative and delta S is positive, right? Let's visualize that really quick. Delta H is negative. That's favorable for a reaction being spontaneous, right? And if delta S is positive, because there's this negative sign here, then at any temperature you throw into this equation, the reaction will be spontaneous. On the other hand, if delta H is positive and delta S is negative, right? So if this is positive and this is negative, then there's no way to get a delta G of anything other than a positive value. No matter what temperature you throw in here, because this is negative, this is going to result in a positive sign plus another positive to be a positive. Okay? So you get this little circle here that shows us that negative delta H, positive delta S, all temperatures is going to be spontaneous. Positive delta H, negative delta S, all temperatures is going to be non-spontaneous. However, if I have a negative delta H, that's favorable, but a negative delta S, which is not favorable towards spontaneity, then at low temperatures, I will be favorable, spontaneous, but at high temperatures, it'll overcome that negative contribution of the delta H and become unfavorable. And the opposite down here with delta H positive and delta S positive. Okay. So, our third law of thermodynamics is simply what we've said already, is that the pure crystalline solid at 0 Kelvin is defined as zero entropy, zero entropy. So delta S is products minus reactants. We should also pay attention to our units. Generally, entropy, that's S, its units are only in joules. Okay, so the table might be different, but because the contribution is always much smaller, right? The work contribution is much smaller in general, then you have to pay attention to the units. Delta H's are usually in kilojoules, while delta S's are generally in joules. All right, so how could we calculate the delta S for a chemical reaction like this? Well, we wouldn't be able to do it unless we were provided S values. But if we have S values, products minus reactants, that positive value should correspond to a reaction that is getting more spontaneous, more disordered. Here we have solid going to gas. Yep, it's expected to have a positive value for that. Okay, now that's kind of frustrating a little bit because we're used to seeing a negative delta H indicating that the reaction is releasing energy. But this equation here solves things with that negative sign. The delta S being positive here times whatever temperature it is results in a negative contribution towards our Gibbs free energy, which should be negative to indicate a spontaneous reaction. All right. Here, S value 213 plus the 40 minus the 92, right? And then this value, again, positive value. We should expect that this reaction is becoming more spontaneous. And yeah, it is, because we see here we start with a solid and we end with a solid, but we also give off some gas. So we have two compounds. One is gaseous. So that's fair to expect that this process releases, gets more random. Therefore, it has a more negative entropy or positive entropy driving force. Okay. Now, can we identify the entropy for this reaction at 500 Kelvin? Can we identify the entropy at 500 Kelvin? So here, on this one here, our answers were 161 joules per mole per Kelvin. Here, our answers, let's see, at 500 Kelvin it shouldn't be per joule per mole per Kelvin. It should be just joule per mole. So we shouldn't have this Kelvin in here. But we can answer this reaction the same way, looking at the magnesium chloride. Magnesium chloride, solid, its entropy contribution, 89.5, right? Plus the water, gaseous, 188.7. And then, why don't we write these down as we go? 89.5, 188.7. All right. That will be our contribution from our products. On the reactant side, we have magnesium oxide, negative 26.9. 26.9. So the product side over here. And then 2 HCl's. Again, this is joules per mole per Kelvin. HCl, 186.7. Okay, so I'll get out my calculator here. 89.5 plus 188.7, 278.2, 26.9 plus 186.7, 213. So I'll go products minus reactants, 64.6. 64.6, and that's kilojoules per mole per Kelvin. But if we're going to do it 500 degrees Kelvin, then we have to multiply that by 500 Kelvin. So I think that this question here, because the answer, whoops, what did we get? 2.1. Oh, did I do that? I did that wrong because I didn't take into account the 2 HCl's, right? 186.7. Oops, sorry about that. So let's try that again. So we got 186.7 times 2 plus the 26.9. There we go, 400.3. So now we'll do our products, 278, minus our reactants, 400.3. So it's a negative 122.1. All right. So important to recognize there the 2 moles. But this isn't at 500 Kelvin. This is just joules per mole per Kelvin. If we wanted to get it at 500, we have to multiply that by 500. All right. One more thing to pay attention to here is S values will always be positive. Right? They'll always be positive. Like Kelvin, they're always going to be positive values. Okay, so delta G naught is dependent on temperature, right? And we can calculate it using delta G of formation data only at 298 Kelvin. If the delta G naught, or delta G naught implies standard conditions, but if concentrations or conditions are not standard, then we have to correct for our delta G. So we can do that using a couple of different approaches. Calculating the delta G at 298 is pretty straightforward because the delta G of formations exist. So here's a chemical reaction. If we want to calculate it for 298 Kelvin, then we can just look at our products. Calcium oxide, negative 604.2. Negative 604.2. Plus carbon dioxide, negative 394.4. That is going to be our products contribution. Whereas our reactants, negative 1128.8. Oh, that reminds me. One other thing that we didn't mention or pay close attention to here is that our answer, again, is in joules. Our answer is in joules. We'll see that later on when we have to combine them. But for these numbers here, for delta H, delta G, and delta H, these values are going to be in kilojoules. So 11, negative 11, 28.8. So let's combine our 604.2 and our 394.4. All right, negative 998.6 product. That's our sum of our products. Minus our reactants. There's just one. 1128.8. So we get a positive 130.2. So products minus reactants is 130.2. And the delta G for this chemical, that's a delta G of a positive value. So that tells us that at 298 Kelvin, room temperature, this reaction, the one that we've seen here, right, we've done the calculations for, is not spontaneous, positive value, right, positive 130.2. So it's not a spontaneous reaction. If we wanted to find out the information at 500 Kelvin, however, what we could do is we could calculate the delta H of the reaction and the delta S of the reaction and use the delta H here minus instead of putting in 298 here, we could put in our 500, the temperature, and multiply it by our delta S, and we'll have to make sure we divide that by 1,000 there. Now, as this was 130 at 298, let's see what happens when we change that to 500 degrees. Let's see if we can get enough of a contribution to make it spontaneous. So, instead of 298 times 0.167, we're going to do 500 times 0.167. All right, and that's going to be a negative or 83.5. But that 83.5 that's the T delta S component, so it's a negative sign in front of there. Delta H is still 178. So this 83.5, that was at 500 degrees Celsius, so we're still not hot enough to get the 178 to result in a positive or negative delta G. So right now we're at 178 minus our 83.5. We're still at positive 94.5. Okay? So, if we wanted to find out what temperature this reaction would be spontaneous at, right? We can take our delta H, 178, it's a positive value, right? But because the delta S is also positive, 0.1607 in terms of kilojoules per mole, 0.1607, that's our delta S. Now we're just going to put T, we're going to put X in here to find out what temperature is necessary, and we'll put in here a 0. Now that temperature will bring it to equilibrium, and then anything slightly higher than that temperature, whatever we solve for here, would make the reaction spontaneous. Okay, so we can solve for this by bringing over our 178, so negative 0.1607 equaling negative 178. Oh, sorry, this is X equaling negative 178. So bring in our calculator. Negative 178 divided by 0.1 oh, negative, yes, negative 0.1607. So at 1,107, when Kelvin equals 1,107.65 degrees, then this reaction will be at equilibrium, and any temperature higher than that, the reaction will become spontaneous. All right? So, if we're given tabulated values for delta G, they'll be at 298, like that. But we can identify the delta G at different temperatures by using delta H and delta S in our second law of thermodynamics. Okay. Let's see. Delta G for reversible reactions. A process is thermodynamic reversible if it can be reversed. The delta G will be 0, right? If you're very close to equilibrium, if it's very close to 0, either negative or positive, then there will be small amounts of both reactants and products on both sides. All right. Let's see then. Well, actually, we're going to skip this. But what's interesting about this is you can actually identify at what temperature this sort of a reaction, copper liquid going to copper solid. Now that's a physical change, right? But what's interesting is if you know the delta H's and the delta G and the entropy contribution of copper in its liquid and in its solid form, you can place delta G at 0 and identify the delta H of a chemical reaction. For example, in this, it's not really a chemical reaction, but you can just say copper solid going to copper liquid, right? Products minus reactions. I can find out the delta H for this if I have the delta H formation for these different components. And I can identify the S, the entropy component. And if I place G at 0, I can solve for T, and what that'll do is it'll tell me the melting point, the temperature at which this process is at equilibrium. And that's the melting point of copper. So, kind of an interesting thing. We won't be doing that sort of thing on the exam, though. Okay, so what is the change in standard free energy? Standard free energy, that's our delta G. What's our change in delta G for this reaction? Okay, at 500 Kelvin. Well, if we want to get the delta G at this reaction at 500 Kelvin, what is it that we have to do? Whose turn is it? I think it's Alyssa's turn. Alyssa, I don't know how long you've been here. Do you feel like you could handle this one? You want to try to approach it, or you want to give someone else a shot?
I didn't think we're sorry. We have some missionaries over for dinner.
That's fine. That's fine.
Is it okay if I watch one more?
Yeah, that's fine. Sarah, do you want to help us out?
Yeah.
All right. So we're trying to use or find out what the Gibbs free energy is, right? Delta G. We'll have this information kind of provided for us. Delta G equals delta H minus T delta S. All right. What can I do to identify the delta G for this reaction?
Hello?
Yeah, Sarah, you there? You there?
I'm not hungry.
Okay. Say that again. Are you there, Sarah?
She can't do it. I can try to do it.
Oh, Sarah's stuck doing something. Well, what do you think, Alyssa? Any ideas?
Well,
How would you find the delta H for this process? Do you know?
You would find the sum of the delta H of the products and the sum of delta H of the reactants.
Yeah, and I think we did this before in these slides last class. So let's go back to this one. Nope, not that one. Back for this one right here. What is the enthalpy of the reaction? So we have this one already. So I'm going to go back here and steal it. Negative 97.3. Negative 97.3. Yep. So
that's products minus reactants, right?
That's right. Products minus reactants. And then
we could find the temperature, which I think it's given.
Yep.
Yeah, 500 Kelvin.
Okay, so negative 97.3 here. 500 Kelvin is going to go there. How do we get our delta S?
Is it also the S of the products minus S of the reactants?
Uh-huh. So, calculator here. What do we got? S, products, magnesium chloride, 89.5. Water.
69.96.
Oh, it's
wait, it's in gas. 188.7.
Okay. That's our sum of our products.
And then reactants are negative 601.7. And 2Cl, so it's 2 times negative 92.3.
Wait a second. Where did we get the 601.7? Oh, that's the delta H. That's the delta H. So we have to make sure where we are on the delta S.
Oh, sorry.
Or the S, yeah. Okay, so 26.9 is for the magnesium oxide plus 186.7. And I'm going to do that twice because we had 2 moles. Okay? Does that look right? So we got products here minus reactants. Negative 122. Is that a reasonable? Yeah, it's okay because we have a solid and a gas on both sides, but here we have 2 moles of gas and we're just going down to 1 mole of gas. So it's negative 122. What do you think, Alyssa? Is that favorable or unfavorable entropically, meaning the entropy? Do you remember? Negative value there for entropy.
It would be favorable, right? Because it can happen with less energy.
Well, actually, here, let's put this into this equation here. Times a negative 122.1.
Positive.
Yeah. So these two values here are multiplied, and then the negative sign is there. So it's actually pushing this delta G towards a more higher positive value. So let's see where we're at then. Negative 122.1. Can I multiply that by 500? I actually shouldn't have written that down so fast. What do I have to change here first, Alyssa?
I'm not sure.
Well, the entropy is in joules, right?
Oh, we have to put it to kilojoules.
Yeah. So divide by 1,000 times, oops, I divided by 10. Divide by 10 to get divided by 1,000. Now I can multiply by my 500. It's 61.5. I'm going to change the sign, though. And I'm going to add it to the negative 97.3. So, still get a negative 36.25. But, yeah, so we're predicting that the reaction is still going to be spontaneous. Still going to be spontaneous, even though the entropy contribution was not entropically spontaneous. Therefore, if we were to raise this temperature and make this contribution higher, there would come a point in which the reaction would actually be non-favorable, unfavorable. Okay. Excellent. How about this? Here's a chemical reaction with a delta H and a delta S provided for us. Is this reaction favored, or same reaction, I guess, is it favored at higher temperatures or lower temperatures? All right, Sarah, are you ready? You got your microphone working?
Yes.
Okay. What do you think? Can we tell whether this reaction is favored at higher or lower temperatures?
I'm sure you can tell, but I don't know.
Okay. Well, it is the same one that we just did over here. So we still have our information. Our delta H was negative 97.3. Our delta S was a 0.1221. And for that last one, our question was, or the temperature was 500. Maybe I should rewrite this a little bit clearer. Delta G equals delta H minus T delta S. And delta H here is a negative 97.3. And the temperature, we'll put a little space for what our temperature that we're going to put in there, but the delta S in kilojoules per mole is negative 0.1221. So these two need to be multiplied by each other before that negative sign goes in there, and then we're going to add it to this negative 97.3. So what happens if this temperature here, this value, gets really large, Sarah? If this gets really large, does that help delta G become negative, or is it causing delta G to become more positive?
So that'll make delta G become more positive.
That's right. If I get a high temperature, the delta G could become more positive and actually more than zero if we got high enough temperature, right? So that would mean that this reaction is not favored at higher temperature. So is the reaction favored at higher or lower temperature? The reaction would have to be favored at lower temperature. See how we did that, Sarah?
Yes.
All right. Okay. So if we're not under standard conditions in terms of concentration, then we do have an alternative way of expressing our or fixing our delta G. If we have delta G naught, we can add to delta G naught an RT ln of our current Q, and we can adjust our delta G naught for non-standard conditions, not just temperature but concentrations, because the Q will take into account different concentrations. So the naught there means room temperature, and it means at constant concentrations of 1 molar for aqueous solutions. Now we're not going to do any of these because there's other fish we want to fry, and this is one of those fish. It's the same thing that we just looked at, but it shows us how we can relate our equilibrium constant K to our delta G. Equilibrium constant K relates to delta G in this way. Delta G naught equals the negative R2 natural log of K. Or if you solve for K, it's E to the, because this is a natural log here, E to the negative delta G RT. Now, thus we can see that if delta G is a large negative number, then K is going to be a large positive value. And that's what this equation shows us, that there is a relationship between delta G and K, and the larger the K, the larger and more negative the delta G. Okay, but that's all we're going to say about that as well. We're not going to be able to go through a lot of these questions kind of at the end of our semester here, our term, right? So let's see what else we want to talk about. We can also think about, and we've talked about this before a little bit, or not a little bit, a lot, that the energy in these chemicals is in the bonds. So when a chemical reaction occurs, you're breaking bonds and forming new bonds. And the bond energy itself can be used to predict whether a reaction is going to release energy or require energy. Specifically heat energy, because heat energy is what is released when you form a bond, and you have to put heat energy in to break a bond. So if we have a list of bond energies like this, and we can look specifically at our chemical reaction and know which bonds are broken and which bonds are formed in the chemical reaction, then we can use the list of energies like this to calculate the delta H for a chemical reaction. So, here's an example. CH4, methane gas, 3 moles of chlorine gas, forming CHCl3, methylene chloride, and 3 HCls. Here, we can, again, look at energy that is being released. That means bonds that are being formed. And that's going to be here on the product side. And we can compare that to energy that's going into the breaking up process, bonds that are being broken, right? Take those energies and, using the same kind of principle, products minus reactants, get our delta H for this chemical reaction without any delta H of formations, right? And these numbers aren't as exact because molecularly bonds kind of can lean on each other a little bit when they're in larger molecules, but it's pretty close, okay? The one thing we do have to do is recognize that because our bond energies are positive here, it's talking about the energy necessary to break the bond. So when we look at this, it's not going to be products minus reactants. It's going to be products or reactants minus products, because we're talking about positive values here, or the energy necessary to break these bonds. So let's take a look here. One thing we can do is just count up the different kinds of bonds we have on the product side and count up the different kinds of bonds we have on the reactant side, find their energies here, and then simply go reactants minus products, and we'll have our delta H for this reaction. We could also just look and see which bonds are broken and which bonds are formed, but sometimes that might be just a little bit, not too difficult, but a little more accounting than we might want to do. Just simplify it and talk about all the bonds that exist. So, in this molecule here, I have a CH bond, another CH bond, a third one, and then a fourth one. So a total of 4 CH bonds. And here I have a chlorine-chlorine bond, but I have 3 moles of this. So I have 3 of these chlorine-chlorine bonds. Those are my reactant bonds. And if I say I need to break all of these bonds and then form, what am I forming? I'm forming one CH4 bond. And you could kind of think of like that. Well, there's only 3 then, right? But it's okay. We just identify all the bonds. One CH bond here, and then 3 of these CCl bonds. And then we have 3 here of these HCl bonds. Okay? So we look at the energies associated with these 4 CH4 bonds. So CH4, 412 kilojoules per mole. So this is 412. There's 4 of them, right? The chlorine-chlorine bond, do we see that one here? Do I see a chlorine-chlorine bond here?
I don't think it's on that list.
It's not on that list. Do we have it? Where do we have? I will have to go to our good friend. What's the energy of a chlorine-chlorine bond? 243. 243 kilojoules per mole. 243 times 3. All right, the carbon-chlorine bond, 338. Oh, here's another carbon-hydrogen bond first, 412. There's just one of those. Carbon-chlorine, 338 times 3. HCl. See HCl here, 431 times 3 also. Okay? So I take all of my bonds here and my bonds here. I'll just do the reactants first here, just to emphasize that here it's not going to be products minus reactants. It's going to be reactants minus products, and we'll talk about, again, we'll review why that's the case after we get our values. But I'll do this first over here. 412 times 4. 3 times 243, and then we'll take this value plus that value, 2,377. Okay, that's the energy on my reactant side. 431 times 3 over here on my product side. 338 times 3 as well, and then 412. So 412 plus this value plus that value. So we're looking at 271.9, 2,719. Not 271.9, 2,719. All right, so I'm adding up all these values here. So to break up all this stuff over here, it would take 2,719. To break up all this stuff over here, it would take 2,377. So it's going to take more energy to break up our products, right? So that means that our products have more energy stored in them, right? So if that's the case, then energy was there's more energy stored here, so our reaction should be a negative. Our change in energy should be a negative value, right? So we take our reactants here, 2,377 minus our 2,719, and the result is our negative 342. So the delta H for this reaction, using our bond energies, is negative 342, which says that this reaction is releases energy in terms of delta H, releases heat energy, it means that the bonds that were formed are stronger than the bonds that we initially had, right? If we thought about this, if we put a negative sign here and said that's how much energy you're going to have to put in to break up these bonds, and put a negative sign here, then we could go products minus reactants, and we would still get the negative 342. Okay? So there's a couple of ways to think about this. One, you can just think about it in terms of bonds and just say products or bond energies, meaning energies necessary to break the bonds, and then go reactants minus products. Or you can put a negative sign in front of them and go products minus reactants. Okay, so let's see here. Here's another problem. We'll finish this one up. This is the, let's see, what we got the last slide here. Yeah. Okay. Here's a chemical reaction. We want to know the delta H from the delta H, calculate delta H from delta H of formation if the delta S bonds have a D bond energy of 225 kilojoules per mole. So that's my sulfur-sulfur bond. The oxygen-oxygen bond, the dissociation energy is 498 kilojoules per mole. And we want to know what the bond dissociation energy for the sulfur oxygen bonds. Okay, the sulfur oxygen bonds. Okay. And we have the delta H of formation here for SO3 being a negative 395.2. The delta H of formation of SO3. So the delta H of formation for SO3, which is this material right here, is 395.2, negative 395.2 kilojoules per moles. And that's what we're seeing here. We're seeing the sulfur, that's elemental sulfur, S8, plus oxygen, elemental oxygen, forming SO3. Now, the delta H of formation isn't for this reaction. This reaction is not a delta H of formation reaction because a delta H of formation reaction needs to, A, form reactants or products from its reactants, from elemental reactants. Yes, that's correct. But the second requirement is that it only forms 1 mole. So like the energy here that's provided is 1 mole of material. But this process here resulted in 8 moles of material. So we can identify the delta H for this reaction as 8 times 395.2. So I have the delta H for this reaction. It's going to be 8 times our negative 395.2. All right. And then that's for this reaction, delta H for this reaction. And then I can identify the delta H using my bonds as well. All right. What bond energy, or how many bonds am I breaking here? Alyssa, how many bonds am I needing to break on my reactant side to get to my products?
Is it 8?
8 of my sulfur-sulfur bonds?
Yes. Yeah. I think so.
Okay, so I have 8 sulfur-sulfur bonds that need to be broken. What else needs to be broken?
I have a question.
Yeah.
So are double bonds, like, are the calculations of a double bond put together, or do you have to include it breaking both bonds?
The double bond is a different value than a single bond. The double bond is not twice the single bond. So,
okay, that was my question.
Yeah. So we have how many of those oxygen-oxygen double bonds do we need to break? 12. 12 of those oxygen-oxygen double bonds. The energy for the oxygen-oxygen double bond, we were told, is 498. The energy for the sulfur-sulfur bond, we were told, is 225. That's the dissociation energy, the energy to break them, right? And on the product side, what bonds are we forming? We're forming sulfur-oxygen bond, sulfur-oxygen double bonds, and we're forming 1, 2, 3, but 8 times. So I have 24 of these sulfur-oxygen double bonds. So it's going to be 24 times whatever the energy is for that sulfur-oxygen double bond. Now I know that in this case, reactants minus products, the way that our bond dissociation energies are positive, I can take my 225 times 8 and my 498 times 12, combine these two together, negative 776, sorry, not negative, 7,776. That's our energy that's stored in our reactant bonds, okay? Our energy stored in our product bonds was going to be represented by our 24x. So reactants minus 24x, all right? And that has to equal the reaction energy for this process. And we already said that this process is going to be the delta H of formation times 8, because 8 moles are found. And now what was that value up here? We got it. Negative 3,161.6. So 7,776 minus 24x should equal our negative 3,161.6. Okay, so let's see if we can get the right answer. Negative 3,161.6 minus 7,776 divided by a negative 24. So our x is 455.7. Okay, so a little review of how we did that. Again, what we did was we took the information associated with our bond energies. We identified how much energy in terms of bonds needed to be broken, right? Solve that value. We identified how much energy was going to be released. We didn't know the S double bond oxygen bond energy, so we just called it X. The energy that was going to be in our reactants bonds minus the energy in the products bonds was going to be the delta H for this reaction. And because we were told that the delta H for a formation for this stuff was negative 395.2, and this is 8 times the delta H of formation reaction, we could set our bond energy information equal to 8 times the delta H of formation and solve for our delta H, our bond energy for our sulfur-oxygen double bond. Okay, very good. Here's one more. It's basically the same thing, so we're not going to do that for now. But it looks like we have finished our chapter, and we have one more class on Monday. So we'll use that day to kind of do a review or go over any problems that people might have, questions that people might have. So make sure you come and bring questions if you come on Monday. I'll advertise that it's going to be kind of a review session to help people remember to bring questions and so forth. Did you guys all see the announcement about the final?
I had a question about that.
Yeah.
Just speculation. If we were to get one wrong and it was 97.5, would that go up to 98?
No, that one wrong would be an A minus, and then you would get an A- worth of points so we can let it relate to how our previous exams were doing, right? So
yeah, sounds good.
yeah, I think everybody who's been kind of keeping up with class will do okay. The problem is this semester we've really had some unknowns that we hadn't dealt with before. And I mean, if people could learn this stuff without going to college, they would have been doing it a long time ago, right? Because nobody likes to sit in class forever and have to learn hard things. But there's some reasons why it's difficult. And there's reasons why people don't always do online classes. And there's a reason why a lot of online colleges go out of business, because it's not a reality. It's maybe someday, but we're having too many students who are just completely bailing out because they get left behind. Some students who were doing well initially, and I don't know how they're doing well without learning, but now they've either stopped trying or aren't doing well anymore. And then we also have